will be given by George Tucker of Google Brain.
Thank you. Hello and welcome. My name is George Tucker, and I'll be presenting Rebar, a gradient estimator that combines ideas from the reinforced method and the concrete distribution, hence the name, to produce low variance and unbiased gradient estimates for stochastic discrete units. This is a joint work with Andriy, Mnih, Maddison, Dieterich, Lawson, and Jascha, Sohl-Dickstein. So discrete stochastic variables appear in many different problems. For example, conditional computation, hard attention in memory networks, generative models, for example, classically sigmoid belief networks, and discrete action reinforcement learning. Generally, learning in these kinds of models requires maximizing a discrete expectation, and computing low variance estimates of the gradient with respect to theta is challenging, as we'll see. So existing gradient estimators come in two flavors. Unbiased estimators can have high variance, which can lead to slow convergence, and mu-propin is previous state-of-the-art approach in this category. And then there are biased estimators, which can have fast convergence, but are biased, so can lead to the wrong solution. And concrete Gumbel-Softmax is an example of a state-of-the-art approach in this category. So we introduce Rebar, a gradient estimator that produces both low variance and unbiased gradient estimates. And it also allows online adaptation of a relaxation temperature hyperparameter that existed in a previous approach. Generally, this leads to faster convergence to better results. So now I'll just go over briefly some of the previous approaches to estimating the gradient of this discrete expectation. First, we have reinforce, which re-expresses the gradient as an expectation, and then we can estimate the expectation with a Monte Carlo sample, which fits nicely with stochastic gradient descent. Unfortunately, the estimator is a very high variance, and if you're familiar with reinforcement learning, this looks like a standard policy gradient estimator. A second approach is to use what's known as the reparameterization trick, and the idea is to reparameterize our discrete variable h as a function g of uniform noise and our parameters. Then what we would typically do is re-express our expectation in terms of the uniform noise, and then we would hope to swap the order of the expectation and the derivative, and typically this produces much lower variance gradient estimates. Unfortunately, because h is discrete, we can't do that here. And Maddison et al. And Jang et al. Introduced the idea of Gumbel-Softmax in concrete to address this problem. So we have our discrete latent variable h, and we can reparameterize it as the heavy side of a continuous variable z, where the heavy side is just the hard threshold function, and I've shown a cartoon depiction of the density of z. And in our case, z is just a logistic random variable, which itself can be reparameterized in terms of a uniform random variable, and our parameter is theta. The obstruction to using the reparameterization trick is the discontinuous heaviside function. And so Maddison et al. Proposed relaxing that heaviside function to a temperature-dependent sigmoid function. And here, this temperature controls the tightness of the relaxation. And then instead of a discrete variable h, we get a continuous approximation to h. And because in this graph, it's continuously differentiable, we can apply the reparameterization trick and get low variance gradient estimates, although they'll be biased due to the approximation. And as we set the temperature closer to 0, the bias goes down, but unfortunately, the variance also goes to infinity. So in practice, we need to balance bias and variance by tuning the temperature. An additional problem with the biased gradients is that they can actually just lead you to the wrong solution. So if you consider this very simple problem where we want to minimize the mean squared error between h and a target value y, You can see that if we follow the concrete gradient estimates, we actually get a suboptimal loss, whereas if we follow unbiased rebar gradients, we converge to the optimal loss. And this, as we'll see later, happens in real problems as well. So now I'll just briefly describe the approach that we took to construct the rebar estimator. So it's a fairly straightforward strategy. What we wanted to do was decompose our objective into a hard and an easy part. So we start with our objective that I talked about, and then we re-express our expectation in terms of the continuous variable. And then we can rewrite our objective in terms of the difference between the discrete model and the continuous model plus the continuous model. And now the second term is continuously differentiable, so we can apply the reparameterization trick to get the gradients that are low variance. And then the first term is more difficult to deal with, so we have to resort to reinforce. But if the approximation is good, this term will be small, and the variance of the gradients will also be small. The temperature parameter T adjusts that relaxation tightness, and it controls the variance between the different terms. So just to summarize, we have our discrete model, which uses Heaviside functions. And what we would like to do is we would like to compute a reparameterization gradient, but unfortunately we can't do that. What we can do, though, is look at a continuous relaxation of the model, compute reparameterization gradients for the continuous relaxation, and then correct with the reinforced gradients from the discrete model and the reinforced gradients for the continuous model. An additional thing that we observed is that the probability of the continuous variable given the discrete variable is actually also itself differentiably reparameterizable. And this allows us to use a technique from the Monte Carlo literature, conditioning, to further reduce the variance. And it's essential for our technique and what's used in the experiments. And roughly the idea is, again, similar. We can re-express our objective as a residual plus a term that we can easily deal with. And you can see the full paper for the details on how this exactly works. Finally, for any temperature, rebar is unbiased, so we can simultaneously minimize the variance of the estimator with respect to the temperature at the same time as optimizing the parameters. And why would we want to do that? Well, rebar is a sum of reinforced gradient terms plus reparameterization trick gradient terms. And we note two points. As the temperature decreases, the variance of the first term decreases, and the variance of the second term increases. And then during training, we noticed that the relative variance between the two terms changes. So it makes sense that we would want to adjust the temperature dynamically as training proceeds. And as you'll see in the experimental results, this improves the performance. So now I'll show some experimental results of an application of rebar to sigmoid belief networks for learning on generative modeling of binarized Mnih digits. In sigmoid belief networks, we have layers of stochastic binary units interspersed with deterministic transformations, in our case, 2 tanh layers or an affine. And we have an approximate inference network going in the reverse direction, as is typical for variational autoencoders. And then we maximize a variational lower bound. So we have, in this plot, we have 2 stochastic layers, 200 nodes, and an affine transformation. And the log, I'm showing the log variance, and you can see that rebar greatly outperforms the previous state-of-the-art approaches. And this generally leads to faster convergence to a better result. And you can see that on the plot here, where rebar with the dynamic temperature is in orange. We also run the experiment with 1 stochastic layer and 200 nodes. And the results are similar, but one thing that's interesting is that in this case, concrete underperforms the unbiased estimators, and we suspect this is due to the bias gradients. We conduct experiments on omniglot and Mnih structured prediction, and again, generally rebar outperforms the other approaches. So in conclusion, Rebar is a gradient estimator that produces low variance, unbiased gradient estimates. It allows online adaptation of relaxation temperature hyperparameters. The code is available online here. And just 2 quick points that recently there's been a paper by William Grathwohl introducing an extension of Rebar called Relax, and code is available at this link. And finally, there's a particularly nice implementation of Rebar and Relax done by a PhD student, Rasmus Bonnevie, at this link. Thank you.
There is time for a few questions. While other people got close to the microphone, I do have a question. Can you say anything about the choice of the parameter t that balances the bias and variance?
Yeah, so that's the nice thing about our approach is that the user doesn't need to set the parameter t, so we can automatically adapt it online in an optimal fashion as the training's proceeding. So that's one of the advantages over the previous approaches. The user doesn't need to set that ahead of time.
Okay, I have a question about this online optimization. How do you compute the gradient with regard to this temperature? And do you have a separate temperature for each discrete variable, or do you have one global temperature?
Yeah, so what we do to compute we compute an estimate of the variance, and then we compute the gradients of the variance. So there's kind of 2 objectives. One objective is the objective that we saw in this talk, and then there's an objective which is minimizing the variance of that estimator. And because it's unbiased for any setting of the temperature, that makes sense to do. And in our experiments, we only used a single global temperature, but it would be reasonable to also have multiple temperatures, and that might perform better.
If there are no more questions, let us thank the speaker again.